Previously, we have explored this side-by-side visualization of superdense coding and quantum teleportation. In this video, we're going to explore an alternative quantum teleportation protocol, which does not require measurement in the sending subroutine. Check out the description to see where you can download the diagrams shown in this video. Here we have a side-by-side visualization of two alternative quantum teleportation protocols. On the left, we have the previously discussed quantum teleportation protocol. And on the right, we have an alternative quantum teleportation protocol without measurement. Both of these protocols can be subdivided into three subroutines, which are called preparation, sending, and receiving. The preparation subroutine is identical for both of these protocols. It is also the same preparation subroutine that is used in super dense coding. The sending subroutine is almost the same for these two quantum teleportation protocols. But the final step in the sending subroutine of the previously discussed protocol contains measurement gates. These measurement gates are omitted in the right diagram. So let's focus on the blue boxes, which contain the sending subroutines. In this left blue box, we can see a controlled NOT gate, followed by a Hadamard gate, and then finally we have two measurement gates. In the right blue box, the controlled NOT gate and the Hadamard gate are present, but the measurement gates are omitted. So we do not have measurement at the end of the sending subroutine. These solid black lines represent qubits. And when you see these double lines, these are representations of classical bits. When a measurement is performed in this left blue box, we take a qubit and we turn it into a classical bit. So measuring a qubit in the computational basis is going to give us either 0 or 1, and that is a classical bit. In this sending procedure on the left, we get two classical bits, and these two classical bits are then sent through a classical channel between the sender's lab and the receiver's lab. The receiver then implements the receiving subroutine, and this subroutine involves a classically controlled bit flip and a classically controlled phase flip. Note that we have double lines present in these symbols for classically controlled gates. So these double lines tell us that it is a classical bit that is controlling this bit flip and this phase flip, which are being applied to qubit 0. But if we go over to the right, we no longer have any classical bits. We have replaced this 2-bit classical channel with a 2-qubit quantum channel. Now we have 2 qubits that are being sent through a quantum channel from the sender's lab to the receiver's lab. And in the receiving subroutine, we no longer have classically controlled gates. These are quantum gates now. We have the controlled NOT gate, where qubit 1 is acting as the control qubit, and qubit 0 is acting as the target qubit. And finally, we have the controlled Z gate. And the controlled Z gate treats qubit 2 as the control and qubit 0 as the target. Now, because this is the controlled Z gate, it actually doesn't matter which one of the qubits we consider to be the control and the target. So the outcome is actually the same. And this notation actually shows us that it doesn't matter which one we call the target and which one we call the control. So we have a black solid circle placed on both of these qubits that are involved in the controlled Z gate operation. But for the controlled NOT gate, it does matter which one is the control and which one is the target. And so the symbol is different. We have a target symbol over the target qubit. If we go back over to the left diagram over here, in the left blue box, we can see those two measurement gates. So qubit 2 is being measured on the left, and qubit 1 is being measured on the right in this blue box. And they are producing those two classical bits. On the right-hand side, in this blue box, we have no measurement gates, and we are keeping these qubits as qubits. So we maintain the state of these qubits as we send them through this quantum channel. And then in the receiver's lab, we have exactly the same state. So this state over here that has this big double sum over here at the very end of the sending procedure, it is exactly the same state that is present in both of these protocols. So before measurement, in this left blue box, we have exactly the same state in both of the protocols. Then, when we perform that measurement, we collapse the state of qubit 2 and qubit 1. And that's where we get those classical bits. And those classical bits contain the information that is used to perform those corrective bit flips and phase flips in the receiving subroutine. So what is a very important difference between these two alternative protocols is that this protocol without measurement omits the measurement gates in the sending subroutine, and it swaps the classical channel for a quantum channel. And it also swaps classically controlled bit flips and phase flips for quantum controlled bit flips and phase flips. We have the controlled NOT and the controlled Z gate present in this receiving procedure. At the very end of the receiving subroutine, we can perform measurements. So in a way, what we're actually doing is moving the measurements from the end of the sending subroutine to the end of the receiving subroutine. And this state psi is a general qubit state that we are trying to teleport in this quantum teleportation protocol. Now that we've seen these two alternative protocols, let's focus on the quantum teleportation protocol without measurement, and let's examine the quantum state at key stages in this alternative protocol. In this purple box at the top, we can see a summary of quantum teleportation without measurement. At the beginning of this protocol, we initialize qubit 1 and qubit 0 in the 2-qubit computational basis state 0, 0. The preparation subroutine is then used to turn this 2-qubit computational basis state into a Bell state. The Bell state is labeled by beta sub 0, 0. This Bell state describes an entangled pair of qubits. The entangled pair of qubits need to be distributed to the sender's lab and the receiver's lab. There is a single qubit quantum channel between the preparer's lab and the sender's lab, and this quantum channel is used to send Q1. Q0 is sent through another single qubit quantum channel between the preparer's lab and the receiver's lab. So that is how we distribute each of these qubits that are in an entangled pair. And that entangled pair is described by this Bell state. So how do we produce that Bell state? Well, we applied a Hadamard gate to qubit 1 and a controlled NOT gate, which treats qubit 1 as the control qubit and qubit 0 as the target qubit. These two gates appear in this summary. They are the first quantum gates to be applied to the initial states of these qubits. So we have H1 and then C1x0. Now that we've seen this preparation subroutine, let's move on to the sending subroutine. At the beginning of the sending subroutine, we initialize Q2, this extra qubit that we have in this lab over here, in the sender's lab. We initialize it in the state psi. Psi is a general qubit state. It is the state that we are trying to teleport. So at the end of the procedure, we want psi to end up in the receiver's lab. So what do we have to do in the sending subroutine? Once we initialize Q2 in the state psi, we have this initial state. So this is the first snapshot of the quantum state in the sending subroutine. We have psi and then beta sub 0, 0. That is the 3-qubit quantum state at the beginning of this sending subroutine. You can see in this summary, we have psi and then 0, 0. So that is because this 0, 0 is at the very beginning of this protocol. And at this stage in the protocol, we have already prepared this Bell state. So that is why we have psi and then this Bell state, beta sub 0, 0. The next quantum gate that we're going to apply is a controlled NOT gate. And this controlled NOT gate treats qubit 2 as the control qubit and qubit 1 as the target. And it is shown over here in this summary. We have C2, X1. And then we're going to apply a Hadamard gate to qubit 2, and that is denoted by H2. And we can also see H2 in this summary. So that produces this final state in the sending subroutine. And at this stage over here, we have exactly the same protocol as the previously discussed quantum teleportation protocol. So this is before measurement. Before measurement, the two protocols are identical. But in this alternative protocol, we're not going to perform a measurement of Q2 and Q1. So there are no measurement gates at the end of the sending subroutine. That means we still have this superposition state over here. So this big double sum at this snapshot is a mathematical description of the quantum state for 3 qubits. We have a 3-qubit system over here. And now, at the end of the sending subroutine, we have 2 qubits that we need to transport. So we need a 2-qubit quantum channel to send 2 qubits from the sender's lab to the receiver's lab. And once these qubits get sent through this 2-qubit quantum channel, all 3 qubits will be in the receiver's lab. So we need the state to remain the same. So the state of this 3-qubit system has to be preserved as these qubits move through a quantum channel. And now, at the beginning of this receiver's lab procedure over here, we have exactly the same state. So this snapshot over here, this mathematical description, that also describes the beginning of this procedure as well. But then we have to apply a controlled NOT gate. And this controlled NOT gate treats qubit 1 as the control qubit and qubit 0 as the target qubit. That is denoted by C1X0. And we can see it appearing over here in the summary at the top. And finally, we have a controlled Z gate. Now the notation for this controlled Z gate is C2Z0. So in this notation, we're implying that qubit 2 is the control qubit and qubit 0 is the target qubit. But because this is the controlled Z gate, we don't actually need to worry about which one is the control and which one is the target. So it doesn't matter. You'll get the same outcome. And that is also shown in the notation, because the notation is the same on both of these qubits. But it is important to specify that qubit 2 and qubit 0 are being involved in this controlled Z gate. So now that we have this gate acting over here, we have the final gate appearing in this summary. So we have a sequence of unitary gates that are acting on this 3-qubit initial state. And that gets us to this final state over here. Now we want to see the mathematical details. Why is this expression over here equivalent to this big double sum? And why do these flips over here, this bit flip and this phase flip, why did they disappear after we apply the controlled X and the controlled Z gate? We're going to see the mathematical details now. In the sending subroutine, we have seen 3 snapshots of the quantum state. Here we have the mathematical details. We can see these quantum states written out in their full form with all of the algebraic manipulations. So these 3 states are identical to the states that we saw in the previously discussed quantum teleportation protocol. We're just going to focus on the final state over here. This final state is where we would perform the measurement in the previously discussed protocol. So we would perform a measurement on Q2 and Q1, and that would give us 2 classical bits. And those classical bits provide us with the information that we need to correct the state of Q0. So we need to correct the state of Q0 because we have this bit flip and phase flip that might be occurring depending on the value of B0 and B1. So that is why we perform the measurement and then send 2 classical bits through a classical channel over to the receiver's lab. But in this alternative quantum teleportation protocol without measurement, we're not going to perform a measurement on Q2 and Q1 Instead, we're going to keep this superposition. So I'm showing all of the details, and we're not just writing this in condensed form, in this summation notation. We're actually seeing the individual terms that appear in this superposition. So let's focus on these last two lines. And now that we have these last two lines, we're going to see how the controlled NOT and the controlled Z gate impact this in the receiving subroutine. In quantum teleportation without measurement, the quantum state at the end of the sending subroutine is described by this expression at the top. This is the same quantum state that is found at the beginning of the receiving subroutine. Let's examine the format of this expression. We have a superposition of four terms. On the left, we have a 2-qubit computational basis state, and we can label that by 2 bits, B1 and B0. So these are the bits in this double sum, and the bits can take on values of either 0 or 1. So that is this left-hand side. But what is going on over here on the right? We have the state psi, and it is getting acted on by Pauli Z raised to the power of B1 and Pauli X raised to the power of B0. This subscript 0 tells us that these Pauli gates are acting on qubit 0. So qubit 0 is furthest to the right, and qubit 2 and qubit 1 are present over here. So going from left to right, we have qubit 2, qubit 1, and then qubit 0. The goal of the receiving subroutine is to get rid of these Pauli gates that are acting on Q0. We want Q0 to just have the state psi. And if we have just the state psi over here, then we will have successfully completed quantum teleportation. So that is the goal. Let's examine the 4 states in this superposition. We have 4 options for the computational basis state on the left. So these options are 0, 0, 0, 1, 1, 0, and 1, 1. On the right, these values of the bits that are present over here, they appear as exponents. And these exponents tell us whether we're applying bit flips and phase flips. So the Pauli X gate corresponds to a bit flip, and the Pauli Z gate corresponds to a phase flip. If the exponent is 0, that means we don't apply it, and if the exponent is 1, it means we do apply it. So let's see how we can get rid of these Pauli gates. First, we're going to apply the controlled NOT gate. And this controlled NOT gate is going to treat qubit 1 as the control and qubit 0 as the target. So that's why we have C1 X0 over here. So Q1 corresponds to the second place. So what we're interested in is the second bit. So the second bit in all of these terms is going to determine whether the controlled NOT gate gets activated. And if the controlled NOT gate is activated, it's going to apply Pauli X to Q0. So let's have a look at the first term. The first term is 0, 0, so it is deactivated. There is no action over here. And the third term is 1, 0. We have a 0 in the second place over here. So this bit is 0, and that means that there is no action. So for the first and the third term, the controlled NOT gate doesn't do anything. But for the second and fourth term, the controlled NOT gate does get activated. It's because we have 0, 1, and then over here we have 1, 1. So that second 1 turns on the controlled NOT gate. And as a result, we end up with another Pauli X gate being applied. So in this top expression, we had x to the power of 1 in those two terms. But now we have x to the power of 2. So we are applying 2 bit flips. And that's the same as applying the identity. Now, all of the Pauli matrices, they are actually equivalent to their inverse. So that means if we square them, it's the same as multiplying by the inverse. And that gives us the identity. So squaring Pauli X and squaring Pauli Z is the same as acting with the identity. And that is the single qubit identity operator. Now, let's have a look at what happens when we get rid of this term. So when we get rid of this x, we're just left with these Pauli z terms. So over here we have z to the power of 0, z to the power of 0, and then we have z to the power of 1 and z to the power of 1. We can get rid of Pauli x because x to the power of 0 is the same as x to the power of 2. That is just the identity. So then we don't need to worry about Pauli x anymore. And that leaves us with this final condensed form. So the only thing that we have now that we need to get rid of is this Pauli z gate. And Pauli z is getting raised to the power of b1. And you can see b1 occurs on the left over here. It is this left bit. So we're going to use this left bit that corresponds to q2 as the control. So now have a look at this final expression at the bottom. We have c2z0. So the control qubit in this context is going to be q2. That's the one on the left. So if that is equal to 1, then we're going to apply a z onto q0. So let's have a look at what happens in these four terms. The first two terms have a 0 as the left bit. So here we have 0, 0 and 0, 1. That means this controlled z gate is not going to do anything. But now let's have a look at these final two terms. We have 1, 0 and 1, 1. So there is a 1 on the left, and that means this controlled z gate gets turned on. So we apply Pauli z onto q0. That gives us z squared and z squared, where we used to just have z to the power of 1. So now we have two phase flips, and those phase flips undo each other, and it's the same as the identity. So we can get rid of all of these Pauli z's because they're all the same as the identity operator acting on the single qubit state psi. And then what we can do is pull out this psi because it is common for all four of these terms. And then we just have a uniform superposition of all of the 2-qubit computational basis states. So 0, 0, 0, 1, 1, 0, and 1, 1 are occurring in this uniform superposition. And we have this normalization coefficient of 2 to the minus 1. So if we measure qubit 0, we are guaranteed to have the same outcomes as if we measured psi in the sender's lab. So if the sender took that state psi and took many iterations and measured the outcomes, you would get a probability distribution. So we would have either 0 or 1 with some probabilities. And those probabilities are determined by those coefficients, alpha sub 0 and alpha sub 1. So those same probabilities are going to be found in this state over here. So if we perform measurements of psi, we're guaranteed to have those same probabilities. But we need to do that many times so that we can actually get a histogram and we can see what the probability of measuring 0 is and what the probability of measuring 1 is. But the important thing is that we have the same quantum state. So even if we don't measure it, we still have the same quantum state that we had in the sender's lab. And we have transported that over to the receiver's lab. But what about the states of Q2 and Q1? What if we measure them at the very end of the receiving subroutine? Well, then we're going to get one of these four options. And these four options, they're actually not a concern for us because we don't actually care about the results of the measurement of Q2 and Q1. We're only interested in the results of measuring Q0. And we want to see if that's consistent with the state being equal to psi. So if we want to verify whether this is indeed psi, we need to perform this protocol many times. And then what we can do is get a histogram. And we can see if the probability of measuring 0 and the probability of measuring 1 is consistent in both the sender's lab and the receiver's lab. Then we can actually experimentally verify whether we have the same state psi. So we have seen the mathematical details. We have seen all of these expressions over here. So these are the mathematical details of the snapshots of the quantum state at 3 stages in the receiving subroutine. And now we have actually seen how this alternative quantum protocol works. We have an alternative protocol for quantum teleportation without measurement. We have removed measurement from the sending subroutine, and we can think of it as actually moving this measurement part to the very end of the receiving subroutine. So only at the very, very end of the protocol do we actually measure the qubits. We keep them as qubits throughout the entire protocol. Now, practically, this may be a little more difficult. It is much easier to send classical bits through a classical channel than to send qubits through a quantum channel, because qubits are very sensitive to noise. But this is a mathematical description of two alternative ways of performing quantum teleportation.